since we talked about mutual inductance, I'm still stuck with that. I would love to use that somehow. So I think I've drawn a figure before. It's a very similar figure. So the two coils I mentioned, right? Let's say this is one coil, the red one. Let's say this is excited using a sinusoidal signal. Okay. So that means there is current flowing through this red winding.
Yes.
And there is a sinusoidal flux which is generated.
Correct.
The one inside is the ferromagnetic core. So there will be some flux lines linking with, maybe I'll choose a different color. So some of the flux lines will link with the other coil also.
Yes.
Correct.
Yes.
So if I measure the voltage here, we may get some voltage depending on the coupling, magnetic coupling between these two coils.
Right. The distance remains the same.
Correct.
Only thing that's moving is the core.
Yeah, yeah. So now if I move the core, let's say this portion, the yellow portion is the core.
Yes.
And this blue part is a non-magnetic material.
Okay.
Let's say I moved this towards this direction.
Okay.
That means, more portion of this winding.
Yes.
Is getting under the influence of the magnetic material.
Yes.
So that means at that time, the link between the center, the red coil and the other coil will increase.
Yes.
So that means the voltage I see here will increase.
Yes, because more flux lines will converge.
Correct.
At that point.
Correct. So it's very similar to what we were discussing here. If we have two coils and if we move them apart, you said the mutual inductance will reduce.
Yes.
And if I bring them close, the mutual inductance will increase.
Right.
So this drawing is just a formal way of doing it or practical way of doing it.
But now you have introduced
a core.
A core and a voltage source.
Yes, yes. Because we didn't like making an electrical connection from a movable coil.
Correct.
So we don't want a moving coil. Yeah. Now I have two fixed coils. I made a mess of all this drawing, but
yes,
it's yeah. So the red coil is excited, and if I measure the voltage induced in this coil, it will be a function of the mutual inductance between these two.
Yes.
Now, earlier we said when I move in one direction, inductance of one of the coils decreases. Why not have one more coil and get the inductance of the other one increases? I think here I was saying when this core comes out, suppose if I have a winding here.
Another winding.
Yeah.
Okay.
And if I measure that inductance also.
Okay.
So in that case, if let's say L1, if it is decreasing, L2 will be increasing.
Okay.
So we talked about that fact few minutes back.
Correct.
So what I'm trying to say is, can I have something like that here also? See here, when I move in this direction, I see an increase in voltage. And when I push the plunger towards the opposite direction, this voltage will decrease.
Yes.
Anyway, this space is free. So I could have one more winding there.
You could. Yes.
Correct, no?
Yes.
Which will have an opposite effect of this winding.
Right. How, in which direction is this wound then? Does that matter?
So that one, right now I am only talking about RMS voltage.
Okay. Okay. Right.
Polarity, we can measure the polarity and accordingly connect, even if it is wound in the
same direction.
Yeah, whether same direction or opposite direction. The terminals are in our hand. we can choose to connect in a way that they are either aiding or opposing.
Right. So what you're trying to say now is, can we add another coil to the
Yeah.
other side?
Yeah. And how will that behave?
Okay.
Something like this.
Okay.
So this one, be excited. And maybe we call this as a primary. Since you said transformer, sounds like it's matching. So, so we have a primary coil. And then the other two, maybe we can call it as secondary coils, right? So maybe P, this is S1 and S2. S1 and S2 are secondary coils, okay? So now what we are saying is, if we move the plunger in this direction, voltage induced in S1 will increase, and that induced in S2 will decrease.
If you move it to the right. If you move
Yeah,
to the right.
yeah, and vice versa.
That's very smart, Bobby. By adding another coil now,
Correct.
you have the opposite effect, but
Yeah,
in the opposite direction.
yeah. Maybe we can say it as a push-pull arrangement.
Right.
Because that way we may be able to avoid effect of some factors that affects both the coils.
Right.
Let's say permeability of the core is reduced
Mhm.
due to increase in temperature or something.
Right.
Then I will have an effect, but both coils will be affected.
Yes, because they are exposed to the same
Correct,
core.
correct. So there may be some way to correct for it.
Yes.
Or the excitation voltage, there is a small change. We may be able to correct for these factors.
So you're saying, depending on the direction it moves, one increases, one decreases, right? Now, what happens when it's in the middle? Exactly in the middle, the core.
I didn't get.
So now you're saying, if it moves to the left, S2 will increase, S1 will decrease.
Correct.
Now, if it moves to the right, S1 will increase, S2 will decrease.
Yeah, voltage induced in these coils.
In this coil.
Yes.
But now, if the core is right at the center, so let's say it has a part of it in S2, part of it in S1.
Correct. So what is the question?
So the question is, so in that case, is it fair to say that S2 is equal to S1?
Oh, S2 will be equal to S1 only when both S1 and S2 see the same amount of
So that's what I'm trying to get at. So that means this is in a place, centered, let's say.
Yeah.
Right?
So maybe I will have a different drawing. So let's say so here onwards I will use the symbols. So let's say this is the P1 winding.
Okay.
Or yeah, P1. Then we have, like you said, two secondaries.
Yes.
And let's say there is a core like this.
Yes.
Maybe slightly bigger. And this can move up or down. So this is, let's say, S1, S2.
Yes.
We can actually have that mutual inductance symbols also. Let's say it's like this.
Okay.
Okay. Now, what was your question? When is, where is zero? Maybe that's what you asked.
Yeah, basically now if both of these were exposed, right, to the same amount of core.
Yeah.
I'm talking about S1 and S2.
Yeah. So that way, that means suppose if I say this is M1, mutual inductance between this and this
Yes.
is M1, and the mutual inductance between the primary and the other secondary is M2.
Yes. Yes.
And we are also saying this is excited using sinusoidally.
Yeah.
Vs.
Yes.
So when we excite, there will be a current, let's say IP, flowing through the primary. So that means the induced voltage in S1, what parameter will be? Maybe Vs1
Okay.
will be IP J omega M1. Because there is a current IP going through this winding. There is a mutual inductance between P1 and S1. So the induced voltage will be that.
Yes.
Similarly, Vs2 will be again
Same current.
yes, J omega M2.
Yes.
Now, like you said, if S1 and S2 see the same amount of core and primary is excited, which is at the center,
Right.
I can get actually output voltage 0 at that position.
Yes, that's what I'm getting at.
Yes, I felt that. So let's say I take V0, output voltage V0 equal to Vs1 minus Vs2.
Yes.
Which can be IP into J omega M1 minus M2.
Yes.
Now, IP is Vs by the impedance of primary.
Correct.
So, we can maybe that also can be written as, let's say, Vs by Rp plus J omega LP. The LP is the primary self-inductance.
Yes.
J, let it be here, omega to M1 minus M2. So, when this is at the center, M1 will be equal to M2.
Right.
So, V0 will be 0.
If you have differential.
Yes. Yes.
The actual value will be the same.
Yeah. I mean, M1 and M2 will be equal.
So, if you minus it, then you get 0.
Yes.
So, that's your center point.
Correct. Now, I can get this V0 directly. I mean, what we have done, it's Vs1 minus Vs2.
Yes.
So, let's say if I take output from here and if I connect here, will I get difference? No. Because this is like connecting two batteries in series.
Yes.
So, that's not a good idea. Let me try something else. Let's say I connect here and get here.
Okay.
So, this will be the difference in voltage.
Yes. That will be 0.
That will be 0 when, I mean, ideally,
in the middle,
when the core is at the center.
So, you make a good point. Because before when I asked you which side it's bound, this diagram is also a nice way to explain that. No?
Correct. Yeah.
You drew the perfect diagram there.
Yeah, now that question or the answer to that question is clearer.
It's much clearer now.
Yes. So, we can also explain this in terms of, I mean, using some maybe waveforms. For example, I mean, suppose if I move in the upward direction and if M1 is more, Vs1 waveform amplitude will be more.
Yes.
Vs2 amplitude will be less. So, when you take difference, you will get an output in phase with Vs1.
Yes.
If it's the other way, you'll get an output in phase with VS2 and so on.
Yes.
So what is advantage? In the sense, see, we have discussed about this resistive sensor. Do you see some benefit out of this? I mean, because there are coils, there are cores.
Absolutely.
Look, it's more complicated.
We've been talking about this problem for a long time.
Correct.
There's no contact.
Okay. So there is no wiper here.
No wiper.
There is no wiper.
There's a core that's just going inside whatever it is, a hollow cylinder or whatever it is.
So the core is free to move.
Yes. So you can forget about your capacitive type.
Yeah. That it will be difficult to sell.
But yeah, the answer to your question is, I think this is the biggest advantage of this. There's no contact.
No contact. So that means the friction loss will also be very low.
Exactly.
Nice. But do you see some problem due to that? Due to that, in the sense, although it is not in contact, I see some mass here. I mean, this guy is not that small.
Yes.
There is some mass.
That's true.
So this may have some effect in the frequency response.
Right.
I mean, for the wiper arrangement, we said 3 Hertz. This will be definitely much more than that. But because of this mass, etc., it may not be able to move. Maybe 25 kilohertz, it may not be able to move.
Yes.
Definitely in the Hertz range, it's perfect.
Yes. And also, as you said, there are still coils, which is
correct.
Some complexity.
Correct. So the main point that you're saying is, it's there is no contact. There is no electrical contact.
Yes.
I'll put it that way.
Yes.
Between the moving part and the fixed parts. They are only magnetically coupled.
Correct.
And what we have made use is the mutual inductance. So far we have only said what? At 0. I mean, when the core is at the center, M1 will be equal to M2 and your output will be 0.
Yes. I mean, the reason I asked you was before when you were explaining, for example, the resistive type, displacement sensor, we were wondering, which direction it was moving.
Yeah.
Right. So for that, you need some sort of a reference.
Correct.
Right. So I was thinking here, okay, you have to.
So now we have got the reference point.
Now we have got the reference point, right? That's important, right? Because otherwise we wouldn't know which direction we're going.
Yes. So now if I measure the, let's say I have connected like this.
Okay.
And then if I'm measuring only the RMS value here, I put a meter here. Let's say I put a RMS reading meter.
Okay.
And then I'll try to plot with respect to X. I change X.
Okay.
As per this equation, I mean, what our understanding here is, this M1 and M2 will move in a push-pull manner.
Yes.
If M1 increases, M2 decreases, and vice versa.
Right.
So that means if I move up, M1 will increase, M2 will decrease. So there will be an increase in output.
Yes.
If I do the other way, also there will be an increase in output.
Right.
Correct? So if I measure the RMS output voltage here, how will that look like? Let's try. I've tried this experiment as usual. So let's say this is 0, X is here, positive side, and I'm measuring the RMS value of the output voltage.
Okay.
Now you have to guide me what kind of output I'll get. At 0?
0.
Okay. And then as X increases, let's say in the positive direction.
Okay.
Output will
increase.
Yes. So this will continue like this, or?
Well, until you see it, that's sports.
Yeah. Because as per this drawing, see, if I move a little bit more in this direction, I mean, there is an increase in M.
Yes.
But after some point, both coils P1 and S1 see the same amount of, the core, whether it moves or not, it is there as
It
it
will
is.
saturate.
It will saturate.
It will saturate. Yes.
So that means I may get increase after some time, it may stop like
Yes.
This is what I actually observed.
Right. This is what you're.
This is what I've seen. At least this portion.
Right.
There is some confusion elsewhere. We'll come to that. What about this side of the X?
Now, if you're taking RMS, then it will also increase
It will
in the opposite direction.
So my drawing will not be proper, but it will be very similar, a mirror image of.
Correct.
Something like this. Correct. But you know, when I actually did this, this 0, I did not get 0.
You didn't get 0.
So the actual curve was something like this. This portion.
Aha. You had some voltage.
I had some voltage even at 0. Other portions, it was smudging like this.
Okay. Now,
whether I repeated? Yeah, I repeated.
And you were sure it was in the middle, no?
Yeah. I kept exactly at the center. Tried all my best levels, but it's not 0. There is something.
But then you have a sinusoidal voltage and you have ferromagnet. Could it be some remnant magnetization?
I don't think so. Because, see, we are exciting, exciting with an AC signal. Its field is produced by an AC alternating magnetic field. There may be a little bit of remnant in the core. It may have some impact. Let's say I removed that also somehow. Okay. Still, I had this problem.
There was an offset, basically.
Yeah, there was an offset.
And it was consistent. It was the same offset that you got every time.
Yeah. So, see, we had this equivalent circuit. We have marked LP, let's say this was S1, so L1, L2, L1 and L2 will be same, and then we had M1 and M2.
Yes.
Do you think, will there be something else? Will there be some other electrical parameters?
Some other electrical parameters.
In the sense, coil will have some resistance.
Oh, that's true.
Will be there.
Yes.
Let's say they are matched.
Okay.
Because I took same length of wire, so it will be same. What else could be there? So you have, let's say, one turn. It's like this, no? So
some space between them.
Some space is there between them.
And you're talking about some capacity.
So there will be some 10 to 10 capacitance.
No matter how tightly you want.
It will only increase that.
Yes, correct.
Yeah.
That's true.
Yeah. So I'm not drawing that way. It may not match exactly, but 10 to 10 I'm not drawing. This winding has got some capacitance.
But you're talking about the windings are generally, we are assuming just one layer.
Yes.
One layer.
Yeah, it could be more layers also. Right. It could be more layers also. So it can be layer to layer,
Layer
or
to
everything put together. Let's say there is some
There's
capacitance.
Okay.
Similarly, this will also have. See, you can match the length of the wire, winding resistance, etc. But this capacitance which is formed while you are manufacturing because of this physical closeness of the winding, turn to turn, etc., it's not precisely in your hand.
Exactly. It's hard to match as well.
Yes. Yeah. So they will not be matched.
Yes.
And now when you send, when a voltage is induced here, we said L1 and L2. So, or when in S1 and S2, we have VS1 and VS2.
Yes.
We have made an open circuit measurement, correct? So, what connection we made is something like this.
Yes, correct.
It's open circuit. So there is no current flowing. No. But now you have this parasitic capacitance. So, there will be some current flowing through this.
And that's what appears.
Yeah. So, our equation was this some constant, which was Vs by Rp plus j omega Lp into omega and so on. And then M1 minus M2. We wrote this assuming that they are in phase or completely out of phase.
Yes.
Correct, no?
Yes.
We have connected in a way that they are out of phase.
Yes.
To achieve the subtraction. But due to this current flow, it need not be exactly out of phase.
So in reality,
yeah. So there will be small phase difference between this VS1 and VS2. So this VS1 minus VS2 need not be 0 when you are physically at 0. Right. When physically the core is at 0.
Yes.
Similarly, there will be some capacitance between this primary and secondary also, because these are windings separated physically.
Yes.
It's an air insulator.
Yes.
So there is inter and intra winding capacitances.
Yes.
So those play some role. Like this, it introduces a small phase difference. Due to that, when you are at 0, you don't get 0 output voltage. So there's a minor, small output voltage even at 0, which is called sometimes the residual voltage.
Residual voltage. So can you deal with this at the back end?
Maybe to some extent. To some extent. The other option is, see, now what we found is there is some phase imbalance between these two voltages.
And that phase imbalance doesn't change?
That doesn't change.
That doesn't change.
Because you have already made the winding, it's fixed.
Right. So that's an advantage.
That's an advantage. Yeah. So you could introduce, some circuit, let's say here. Let's say along with this parasitic capacitance, I introduce something else.
Okay.
And let's say due to this capacitance, there was a phase increase in the phase.
Okay.
I introduce this in a way that there is a decrease in the phase.
Okay, to match that.
Yeah. So we forget what the circuit is.
Right.
But let's say we introduce something like that, a phase correction circuit. And I keep the core exactly at the center, adjust this one such a way that at 0 I get 0.
Right. So some potentiometer, so you get
Correct. It is possible.
Right. It is possible.
It is possible.
Right. So this is basically you're calibrating your
Yes.
in a way.
Yes. So it could be even let's say a capacitor, like you said, and a resistor like this. So this introduces a phase. Let's say this is your VS1, and if you take output here, there will be a phase change. I can make use of that. Or I can, instead of C and R like this, I can have R here and C here. Okay. So I can have a phase leading or phase lagging circuit.
Okay.
Because here the current will be leading this voltage.
Yes.
So that means the voltage across this will lead Vs1 by a bit.
Yes.
While here it will be lagging. So we could introduce this kind of phase lag or phase lead or phase lag circuits to have this correction.
So some sort of a compensation.
Yes. It's a common set.
But do we have to have this for both coils?
Actually, some people do it in a smart way. They connect in a way that when you, let's say, vary this parameter R, it has a push-pull arrangement.
It cancels.
When you correct for one, when you advance one coil,
right,
you lag the other coil. So the correction is faster. Probably we'll see soon, something like that. Yeah. But there is a catch here. Because if you look at the equation, you have Vs. Let's say we maintain that. But there is some omega also.
Yes.
So what correction that you are doing, this phase correction that you are doing, is for some particular frequency. If frequency changes, then you have problem. Right?
So it's not so straightforward.
Yes. There is also one more factor. Suppose, see, this guy is a what material? Ferromagnetic material.
That is, for me, or she could also change the frequency.
Yeah.
Yes.
And that is correct. But there is additional factor. I don't know. You know this. I don't know whether students have studied this, but they may know the characteristic like this for a ferromagnetic material.
BH curve.
Yeah.
Yes.
Or the full hysteresis loop itself. Yeah. Right? So B is here and H is here. So this is not a straight line. No. So which means if you mentioned transformer, the no load current of a transformer, if you observe, is not sine wave. No. It has got some other components. Similarly here, when you have core made of ferromagnetic material like this, although you are giving a sinusoidal voltage here, the current drawn from this is not pure sinusoid. Okay. Because of this non-linear characteristic of the core. Yes. Anything non-linear will introduce some harmonics in the system. Yes. Now, that means the IP that we have drawn here, here, it is not just for omega. There will be third harmonics also.
Right.
So there will be 3 omega present. Right?
Right.
The correction that I am doing is for omega.
But then there could be...
Yeah. I cannot use the same resistor and capacitor to correct for 2 frequencies. So you can correct this only for fundamental. Right? So that means I can bring down, but it will not be exactly 0.
Yes. You can bring down the fundamental frequency, right, but then there are also higher harmonics.
Correct. Of course, there's a secondary effect or second order effect.
Yes. Could be smaller.
Yeah.
Right? But still,
yes.
Yeah, you're saying it's not exactly 0.
Yes.
That's what you're trying to say.
Yes. So what we have learned is, what we understood is, this arrangement is good. No friction or friction is very, very low. It will have a long lifespan, etc. And then we try to plot this output versus X. We see some characteristic like this. And from here, what we feel is, probably we can use some range of it.
Linear region.
Yes.
Yes.
To getting the output. Yes. But you had a question, how we will differentiate between, let's say
How do you know if
yes,
going left or right?
correct. Let's say at some point I get this output.
Yeah.
I get the same output here also.
So what is X then?
So I don't know whether I'm here or here.
Exactly.
So this is a question. So the polarity is lost if you are just measuring RMS value.
Yeah. Well, you don't know where you are. It's increasing, but
Correct.
it's increasing for both sides.
Correct. It could be plus 5 mm or minus 5 mm.
Right.
You get same output
Right.
voltage. Yeah. So your question about the polarity,
Yes.
whether X is positive or negative, how we will know?
Yes. Which direction are we going?
Yes. So this means I cannot simply measure the RMS of the difference.
No.
This is not enough.
Yes. You get the same voltage for both directions,
Correct.
which is a problem.
What to do now? What if I measure separately? Here I have connected like this, connected in phase opposition. And then suppose if I measure this and this and then subtract, will it help?
Even if you subtract, how will you know the direction? You get a value.
Or let's say I'll draw typical VS1 and VS2 here. Let's say X equal to 0. They are like this.
Yes.
Let's say they both have same magnitude.
Okay.
Then let's say M is increased. I'll draw it in a red color. M1 is increased. That means this went up.
Okay.
Not proper drawing, but I guess you try to make out.
So this goes down.
This goes down. So if I measure RMS value separately, I will know VS1 is greater than VS2.
Correct. If you're pushing it in a certain direction that you're aware of.
Or VS1 will be greater than VS2 only if X is positive.
Positive. Okay. Okay. You defined that side as a positive side.
Yeah.
Okay.
And the other way means if X is negative, M1, let's say, decreased.
Yes.
And in this case, it will increase.
Correct.
So that means VS2 will become higher than VS1.
So then you know you're going the opposite direction. Correct. Because you have reference point.
Correct.
Yes.
So somehow we have that polarity electrically now.
Yes. So yes. So the question, the answer to your question is yes, you can.
Correct.
Yes.
Well, so making two measurements, subtracting is not the best idea.
It's not a very elegant way of doing it.
Yes. Also, I think we are not supposed to measure two quantities which are almost equal and subtract them. Because that will be full of error.
Right.
Correct, no?
Yes. You're making two separate measurements now.
Yes. So, or for example, when M is 0, let's say this is 1 volt. Example. This is also 1 volt. Let's say the meter I am using is maybe 1% accuracy. Right?
Unless you measure it separately, write it down and use the same meter.
Yeah.
But that's not what you're
Even then it can be
random.
Even then. There can be random error.
That's true.
So what I subtract and get will be full of error.
Yes.
At 0.
Yeah.
So maybe we will take that example a little bit more clearer later. But anyway, two quantities of almost equal range, while use, we never measure them and then subtract to get a final output.
Yes. Yes.
Because the error that is propagated can be very large.
Right.
But what we see is if you do something like that, or if you can retain this information, then you will be able to get it.